All right, let's do an example of reactions on a machine. We have here, if you see it, this hoist system over here that's on a pin support against this vertical wall at A. It's got a roller on a horizontal surface down here at B. And then it's got a motor up here at this point that is going up and over C and then coming down connected to the bottom of this cart. This cart is 1 foot tall and it weighs 5 kips or 5,000 pounds. And this incline that it's rolling up is 60 degrees to the horizontal. If we assume that all the rollers and wheels and pulleys and everything are all frictionless, let's determine all the reactions. That's what we're tasked with doing in this example. So I guess, before we can calculate the reactions, we got to draw the reactions. To do that, we need to sit down and think, all right, well, where would they be? And I would say, first off, I guess there's this vertical one at B. You know that because this is a roller on a horizontal surface, which means it's got a vertical reaction, always normal to the surface it's rolling on. So we can call this our B. A over there has a pin support, so there's going to be 2 reaction vectors. There's going to be one vertical and one horizontal. I am guessing, I don't have to be right, but I'm guessing that this reaction, the vertical reaction A, is going to be holding this whole hoist down because it looks like it's going to want to roll clockwise if this cart were to pull it down. So I'm thinking that this reaction here is going to be acting downward. Again, if I'm wrong, I'll just get a negative number, no big deal. So I'll call this RAY. And then I think the horizontal reaction is going to be pointing to the left. Again, if I'm wrong, no big deal. So we'll call that one RAX. So those are our reactions on the hoist. We still have a few more reactions, a couple. In fact, we have them down there on the cart, don't we? Because the cart is rolling against a surface. So those are also roller supports, and that means we're going to have perpendicular to that surface, and that's going to be R, so D we'll call it, and then we have one more here at E. So I think those are all of our reaction vectors, 1, 2, 3, 4, 5. So we can't just solve for these reactions looking at this overall structure because there's 5 unknowns and we'd only have 3 equations of equilibrium, right? Sum of forces in the X and sum of forces in the Y and sum of moments. So we need to break this up and we need to be thinking, what's our N here? And, I think the most obvious choice is that cable is either going to be in tension or compression, right? And cables are always in tension. So we know that this cable right here is going to be in tension. So we know what the internal force direction is. We just don't know the magnitude. I think if we cut a free body diagram of just the cart, that will be our way into the problem. We could solve then for R sub D and R sub E, and then we could go back to our main overall structure and start solving for these other reactions. So here's the free body diagram of this cart. I've kept the part that I am keeping, which is the cart itself, the weight of the cart, the reactions of the ground against the cart, R sub D and R sub E, the 60-degree incline. I've gotten rid of the parts that I'm getting rid of, the hoist and everything else. And then at the cut surface, I have placed the internal force that is going to develop, which would be that tension right there. So I've got a nice free body here. It's got all the dimensions I need. I can work with this, okay? Now, if I had kept my X and Y axes as they are globally for the problem, X pointing to the right and Y pointing up, that would be kind of problematic. It wouldn't be the end of the world. I mean, you can still work with it, but it's not aligned. The cart's not aligned to that. So it's kind of clunky. So I have made a new set of axes here just for this free body, and I've called them X prime and Y prime. The prime, just differentiates it from the normal set of axes. So I'm going to be dealing with the X prime and Y prime axes here. So, I guess the origin of this X prime and Y prime would be over there where the wheel at D is hitting the ground. All right. And so I'm just going to be working with those for this free body. And then I can shift back to the regular X and Y when I get what I want from this free body. Okay. So if I had kept my X and Y horizontal and vertical, RD, RE, and T would all have components, and all of them would be really messy. Now I think you can see that if I'm looking at this problem, I might be able to isolate this pretty well if I go in with a particular direction of force. So I'm going to say let's do sum of forces in X prime, because then you can see that the only things that are happening in X prime are the X prime component of the 5 kip weight and then the tension. So RD and RE are not acting in the X prime. So that's what's going to be really cool about that equation. Okay, so before I get started with that equation, I guess I really need to be thinking about what that X prime component of the 5 kip load is. So, you know, these things acting on a slope, it always gets a little kind of hard to mess with the angles. You got to be thinking about what's going on here. If we had this vertical line right here, and that's vertical, and here's horizontal, our 60-degree angle is this one right here, isn't it? If we were to look at the opposite angle over here, that makes this one 60 degrees, which makes this one right here 30 degrees. I think that gives us what we need, because then we can say that, well, the y prime component of the 5 kip load is going to be 5 kips times the sine of 30 degrees, and the x prime component is going to be times the cosine of 30 degrees. Okay, so I'm going to get rid of some of this just to make it easier to see in the long run. Just keep in mind that your free body diagrams are meant to be like a work surface, you know, like scribble on them, doodle on them, you know, figure this stuff out. So I am now going to say, well, in the spirit of doodling and figuring things out, I'm going to go ahead and write those components on here. So I would have my y prime component of force be that one, and my x prime component of force be that one. Okay, so this one here is 5 kips times the cosine of 30 degrees, or 4.33 kips. 4.330 if you want to have 4 significant figures. And then the other one in the y prime, this one right here, is going to be 5 times the sine of 30 degrees, 2.5 kips even. Okay, so now we've got, you know, some useful information here. I think we've got a really nice free body that we can go and do a bit more work with and start building our equations. So let's do that. We've got x prime, y prime, and the moment about the z in any direction. So let's do that x prime direction. I'm going to say sum of forces in the x prime, and I'll say the positive x prime direction is positive. You know, pointing down and to the right is positive, equals 0. So then what do I have? Well, the only things I have are the 4.33 kip force and the tension here. So I'm going to have 4.33 kips minus T equals 0. So that tells me that the tension in the cable is 4.33 kips. So that's really cool. And I can put that up here using my free body to update it to, you know, to help inform my next steps. I can't do sum of forces in the y prime yet because r sub d and r sub e are both acting in that direction. So I'm kind of out of luck. I can't even say that they're, you know, some people might say, well, aren't they equal? They're each half of 2.5 kips. No, that's not absolutely true. The 2.5 is only that y prime component. We also have this 4.33 kips, which is causing some moment. So, you know, just my gut is telling me that r sub e, this wheel up here, is going to have a heavier load on it than r sub d because it's wanting to roll clockwise. The whole cart wants to kind of rotate clockwise. So that's just my gut telling me. My equation will prove it. So let's go ahead and say sum of moments about, and I'm going to sum moments about this point right here, F. And I labeled that as an additional point. You can always label additional points as you need. The reason I'm picking that one is because, remember, some of moments you want to pick a very easy point. You want to pick the point that has the most things going through it that you either don't need to consider or you don't care about considering, or just making your equations as simple as possible. So if I go through point F there, then R sub D is not going to enter my equation. It's going to leave the only unknown to be R sub E. So I can solve for R sub E with this equation. So sum of moments about F equal to 0, and I'm saying counterclockwise is positive. R sub D won't be in there. The tension in the cable won't be in there too, because the cable is attached to the bottom of the cart there. So what is going to be in there? Well, the 2.5 kip Y prime force, and that's going to be times 1 foot. And that's a clockwise moment, right? So that's going to be negative. It's wanting to cause a clockwise moment about F, a clockwise rotation about F, so it will be negative. We've got the X prime component of the force as well, 4.33 kips, and that's going to be times 0.5 feet there, 6 inches or 0.5 feet. And that's also going to be minus, right? Because it's also causing a clockwise rotation. And then I'm going to have plus R sub E, and that's times 2 feet equals 0. So R sub E is going to equal 2.333 kips if we keep our 4 significant figures. So I can put that on here. That's equal to 2.333 kips. So now I can sum forces in the Y prime and get R sub D. And that's going to be positive Y prime is positive. So I'm going to have R sub D minus 2.5 kips, the Y prime component of the 5 kip weight, plus R sub E, which is not R sub E anymore, right? It's got a number. It's 2.333 kips. I mean, it is R sub E, but why call it a letter when you can call it a number? It goes into your calculator so much more easily. That's equal to 0. R sub D is equal to 0.167 kips. So as I was saying, I think my assessment was correct in that R sub E had a much larger force because of the rotation that wanted to happen. And the free body diagram proved it, and we've got these numbers that we need. And what we can take from this is, keep in mind, if we find a reaction on a free body, it also, if that reaction shows up on any other free body, then we already know that value. So we actually have solved for these 2 reactions. Those are 2 of the answers we need, right? So these 2 things are answers. So that's cool. We can put them back on our big structure as well. So why don't we do that? So we know now that R sub E is equal to 2.333 kips, and R sub D is equal to 0.167 kips. So now we should be in a lot better shape. We also know the tension in the cable, which is 4.333 kips. And since we know that, I might end up cutting just a free body of just the hoist later.